Okay, welcome. This is a video to show the exception to the claim that the mixed partial derivatives are always equal, or Clairaut's theorem. Now, let's get to it. And we'll go ahead and get started if I can get this to work. There we go. All right, so in 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 many cases, I should say, for as I say, for the usual functions, and usual I'm going to put in quotes. I'm not going to be precise about that. Functions of two variables. We have that the mixed partial, if you take the partial with respect to x and then with y, is equal to f of yx. Now the hypothesis, I'm not going to be proving this theorem, but this is going to be true when the second partials are continuous in some open disk containing x naught and y naught in its interior. Now, if you want to get into the weeds or you want to get into the whys for that, that's a great reason to take some advanced calculus and learn a little bit about Taylor series for two variable functions. But, there's a reason for this hypothesis. And so let's go ahead and look for a case where Clairaut's theorem does not apply. And so this is a textbook example. You see these in math textbooks. But suppose you have f of xy equal, and then it's going to be x cubed y minus, it's going to be xy cubed. There is a deliberate symmetry on here, over x squared plus y squared away from the origin, and let this equal 0 at the origin. Now, the very first thing, so if this is f sub x and y, we would like to see what the first partials are. So if I take a look at f sub x, and let's go ahead and exclude this being the origin, what we can do is we can treat this just like a basic partial derivatives question, because it is. The only bad point is 0, 0. So we are in a quotient rule situation. So we would square the denominator, and then we take the partial of this with respect to x, which is 3x squared y minus y cubed times the bottom minus the derivative of the denominator times the entire numerator. Now, I'm not going to belabor the algebra, because if you're interested in this particular theorem, you're probably reasonably comfortable with doing algebra. So I'll go through that kind of quickly. So the first partial, you're going to have 3x to the fourth y, that's multiplying these two, minus y cubed x squared plus 3x squared y cubed. Notice how that's conveniently there. Minus y to the fifth, that's important. Minus 2x fourth y plus 2x squared y cubed all over that denominator. And then we can just, we can consolidate some terms here. We have 3 minus 2, so this is equal to, using this terms, those two terms, there's x fourth y, so it's x fourth y. Then we have these two, which give you a 2x squared y cubed, plus another 2x squared y cubed. Minus y to the fifth, all over x squared plus y squared square. Now this is f of x, the partial with respect to x, xy not equal to 0, 0. All right. Now that's important. Now, by symmetry, by inverse symmetry, we for xy not the origin, the partial with respect to y is that we take the negative of everything. And remember, there's a skew symmetry here. The original function, if you replace, if you swap the x's and y's, what happens is you get the negative of this. So all we have to do is swap x's and y's and change the sign. So this will be x to the fifth. And this part here would be minus 4 y squared x cubed. And let's see here, did I make a sign error? So we have a minus 2x fourth. Yeah, no, I didn't. And okay, there we go. Just doing a double check. Yep. And then we have a minus x y to the fourth. So we just basically did that. So that's going to be important. Now, I think I should probably, just for good form, let's calculate the first partial at 0, 0. Now that, I'm going to go ahead and revert to that function there. This will be the limit, change in x goes to 0. And let's keep in mind, f of 0, 0 is defined to be 0 right here. So we'll just keep that in mind. But this is going to be f of 0 plus change in x, 0 minus f 0, 0 over delta x. And just keeping this in mind right here, this will be the limit as delta x goes to 0, delta x. And then this thing right here, 0 plus delta x. So it's 0 plus delta x cubed, y is 0, minus 0 plus delta x times 0 cubed, all divided by delta x squared plus 0 minus 0. This is in the denominator. And notice the numerator here. You have a 0 multiplied by delta x. So that's a 0, because remember, delta x isn't actually 0 yet. And that's delta x cubed times 0. So the first partial is going to be 0 at xy equal the origin. And similarly, by the same calculation, that's going to be 0 as well. So we do have first partials. I'm not going to comment on the continuity of it. What I am going to do is I am going to talk about now the mixed partials. So let's take a look. That is, remember, the partial of f with respect to x when we're not exactly at the origin. So now let's calculate this right here. Let's calculate f sub xy at the origin. Well, that's going to be the limit as delta y now goes to 0 of the first partial of x at 0, 0 plus change in y, minus f sub x at 0, 0. See, this is why we needed that. Delta y. Now let's keep in mind what that is. This part here, we already calculated that's going to be 0. What we're going to do here now is we're going to plug in 0 and 0 plus delta y into this function here. So this will be doing the appropriate plug-in. And just remember, I did have this here. I'm going to be plugging into that. I am going to be plugging in x equals 0. So 0 to the fourth. My y is going to be 0 plus delta y plus same thing here, 4 0 squared and we don't really even need to write that down, but 0 plus delta y cubed minus 0 plus delta y to the fifth, all minus 0. Oh yeah, and yeah, now this part here, I remember that's going to be squared, so that's going to be 0 squared plus 0 plus delta y squared, quantity squared, and then all of this is the f sub 0, 0 over delta y. Now let's take a look at what that is. That's a 0. That's a 0. This is delta y to the fifth, negative delta y to the fifth. This bottom here is delta y to the fourth, all over delta y. And that's going to be the limit as delta y goes to 0 of minus delta y to the fifth over delta y to the fifth, combining these two, and that's negative 1. All right? On the other hand, by symmetry, because remember now, we had this situation here, so I'm going to go ahead and do this quickly. If I want to calculate now f sub yx at 0, 0, what I have is a limit as delta x goes to 0. And remember, you do have the negative symmetry here. So that's going to be the 0 plus delta x to the fifth, but that gets a positive, minus 4. And that's going to be swapping this out here. It's going to be delta x squared, 0 plus delta x cubed. So it's delta y. I'm sorry, yeah. That's a 0 there. I screwed that up a little bit. So this is the x here. So you still get the 0 squared there. And let's see. Now let's just double check that. All right. So it's 4 0 squared delta x cubed. Right. Minus 0 to the 4th delta x all over delta x squared, because I put in the 0 here, squared over delta x. So now notice the sign there. And it's a sign that's important. Notice the sign right here. The sign is positive. So we get the limit as delta x goes to 0 of delta x to the 5th divided by delta x to the 4th, all divided by, that's a 4, not a 9, delta x. And then we get delta x to the 5th over delta x to the 5th, and that's positive 1. So we see that f of yx at 0, 0 is not equal to f of xy at 0, 0. So Clairaut's theorem does not apply, and the reason is that the second partials are not continuous at the origin. So the theorem itself is not violated if the hypothesis does not apply. So I'll just clear this up and indicate does not apply. Second partials are not continuous. So that's what I have, and thanks for watching.